afternoon. Welcome to the 2023 Holiday Science Lecture. It's a pleasure for us to welcome you here to Princeton University. My name is Howard Stone. I'll be joined up front by a number of my colleagues for this presentation, which was put together by a group from Princeton University and Harvard University. So first I should ask, is everyone looking forward to the holiday season? Oh, so a couple announcements. The program is about 65 minutes. A couple times during the show, we're going to ask kids to come down and help us act out what the science is all about. If you'd like your child to be able to do that, just send them down. And if you don't, that's fine too. And finally, the goal is have fun, learn something, and participate with us. Okay, that's the goal. All right, so the topic is about patterns. Looking around the room, I see a gentleman here with a nice pattern on his shirt. If you look close, actually, I have a pattern on my shirt. There are patterns lots of places. You've got nice stripes on your shirt, young man. It's great. So we're going to try to illustrate this to you in a wide range of situations and convince you that the world is amazing. There are going to be some ideas you've probably seen before, and I think for many in the audience, there'll be some ideas you've never seen before. That hopefully is the case. And we get to illustrate how scientists and engineers think about the world. There's no better place to start than this man. His name? Albert Einstein, one of the great intellectuals of the 20th century. This is what he had to say. In the matter of science, the first lesson should contain nothing but what is experimental and interesting to see. Albert looks pretty serious there, but he had a fun side. And if you've been to the Thomas Sweet ice cream parlor, you know he liked ice cream. Okay? So that's a nice way to think about the holidays. So our goal is to illustrate things for you. We asked when you signed up to send us what you thought about, a word or two that you thought about. When you heard the word pattern or pattern formation, this is what you told us, this set of words. During this presentation, you're going to hear about symmetry. You're going to see a little about snowflakes. You're going to hear the word pentagon. There's going to be some geometry. You'll see a lot about nature. If you pay careful attention, the word cryptography will appear once. So there are lots of the words on this slide you'll see during this talk, which spans all kinds of ways that patterns appear in our everyday life, from breakfast to nature to whatever. Okay, so when I think about, maybe I should ask you, what do you think about when you hear the word pattern? Maybe one of the kids in the audience. Yeah?
Pattern means something, I think it means like something repeated over and over again.
Yeah, a pattern is something that repeats over and over again. That's a pretty good definition, I think. And so that's actually what we thought about when we were thinking about what are the patterns we see in our everyday life. So here's a fly. Do some of you like flies? Do you not like flies? Well, okay, so here's a fly, and if you look at the eye of the fly, this is what it looks like if you look at it with a pretty powerful microscope, and you see it has a pattern to it. Can you see how many sides many of these polygons have? If you look closely, you'll see many of them have 6 sides. What do we call a 6-sided shape? Young man? A hexagon. So during this talk, you're going to see hexagons a lot. They appear in many, many different places. But those aren't the only patterns that appear. If you go to the desert and you have a sandy environment with wind blowing over it, you tend to get patterns like this. And how might you describe that to somebody? What's the kind of pattern you see? What's the structure you see?
Like stripe?
Yes, you see stripe-like things. What were you going to say? Wave. Yeah, you see a wave-like thing or stripe-like structure. So that's what a scientist says. You see stripe-like features. And in fact, if you go to the ocean, often when you have water going over a sandy bottom, you get a stripe-like structure. And if you're really attentive in the image, you see that there's an optical feature from the sunlight that creates a different kind of pattern. So there are many different places where you can look for patterns. Okay, if you're a scientist and you want to explain things, often you start with this chart. This chart is called the periodic table. It says it on the slide, so, okay, it's not exactly a quiz. But all right, so we have to do a little, see how you're doing in school for the kids and for the parents, what you remember, if anything, from school. We'll do our best. What's He? Helium. And what's C? Carbon. Okay, you're doing pretty well. What's H? Oh, good. N? P? Princeton. Okay, we're in Princeton, New Jersey. We're at Princeton University. P is for Princeton, but if you read, you can see P is the symbol for phosphorus, and O is oxygen. Okay, so these are the building blocks of nature. This is what, if a scientist has to start somewhere, often, not always, they'll start here. And so they think about the atoms that make up the world, and if you put atoms together, you get small molecules. They're very common ones that are important for life. Hydrogen as a gas that's now talked about as a fuel for what's called the hydrogen economy. We all breathe in oxygen and we breathe out carbon dioxide. Those are part of the gases that are part of life. And if you put molecules together, you get bigger structures. Table salt forms a crystalline solid you have on your table. It forms a solid, a crystalline structure that's a little like this. If you look for a pattern here, you might draw a picture of connecting the centers of those little spheres with lines, and you might say you have a square-like pattern. That's what you might say, or a cube-like pattern. Now, lest you think this is all simple, the world's best scientists often use very powerful machines, microscopes, to look at the smallest things that you can possibly visualize because they want to do better than just an artist. And so I'm not going to show you something that's small. Here's how small it is. It's a microscope that's used to try to image atoms. To get the scale, to get the size right, what I need you to think about is a typical human hair for those of you fortunate enough to have yours. You and I are on the bad side of that. Okay, so if you take a human hair along its width, its diameter, and break it up into 100,000 small bits, really small, 100,000 small bits, you would see the space between two atoms. And this image from Professor Leslie Shoup in chemistry and Sang-Feng Wu in physics is imaging a kind of metallic-like material, and they're trying to understand at the scale of individual atoms what goes on. So this is one of the best images you can get at the smallest scales visible in nature. Okay, when you think about winter, what do you think about? Snowflakes. So snowflakes are crystals, and a typical snowflake is associated with how many little points? It's a six-sided object. What do we call a six-sided object? Hexagon. So snowflakes have what are called a hexagonal structure. These images were made more than 100 years ago by the first person who tried to document the shapes of snowflakes. His name was Wilson Bentley. If you're interested more about him, he was a very creative photographer who was trying to ask questions like, you know, are all snowflakes the same? What do crystals look like? And so he lived in Vermont. Here he is. He was trying to innovate in photography. Vermont is Jericho, Vermont, where he lived and worked, is up here. Princeton, we're down there. Jericho gets a lot of snow, so I guess it was a natural thing for someone who liked photography to use snowflakes. And if you're interested in his photography, he made thousands of images, and many of them are in the Smithsonian in Washington, D.C., if you happen to get down there and you want to know a little bit more about the history of this. Okay, so he was interested in snowflakes, and other crystals have other shapes, so we have to learn some of the language of simple shapes. So you guys are going to help me with this. If you have a three-sided shape, what do you call it? A triangle. Okay, you got the first one right. Let's see how we do. Four-sided shape? Square, when all the sides are the same. If the sides have different shapes, what do you call it? Rectangle. Okay, that's a rectangle. You're doing pretty well. Now, the next ones are to trick you. So the five-sided shape is called a... Pretty good, okay. We already know what a 6-sided shape is. It's a hexagon, but you guys aren't going to get the 8-sided shape. Octagon. Okay, great. All right, so we know the simple shapes, simple planar shapes, okay? That's the language we use to talk about them. Many crystals are three-dimensional, so three-dimensional shapes have similar characteristics. You can have shapes that are effectively like squares. We refer to them as cubic crystals. Sodium chloride, your table salt, is an example. You can have shapes that are more rectangular in structure. Those have different names depending on things. And you can, if you remember the pyramids, you can have shapes that are pyramidal, and they have 4 sides on the top and 4 at the bottom, so they have 8 sides, so we refer to them as octahedrons. There are many different kinds of crystals. And to illustrate to you different crystals and one or two wonderful things, my colleague Samantha McBride is going to tell you a little about a couple experiments she's going to do with Janine Nunes, and you get to see this.
So we have a solution of salt water. So the same type of salt that you put in your food. Now this is super salty, about 10 times the concentration of ocean water. And so what we're going to do is we're going to take a drop of this super salty water and just evaporate it using this hot plate set to 90 degrees Celsius. So that's going to take a few minutes to evaporate. So while we wait, we're also going to do an experiment with sodium acetate. So sodium acetate has some different properties than sodium chloride, even though they both have sodium. So what Janine is going to do is she's going to open this bottle of saturated sodium acetate, and she's going to drop a seed crystal, so an existing crystal of the solution inside, and we're going to see as the crystals actually start to form. So there goes the crystal. Great. So who wants to yell out what type of shape they see? Yeah? Oh, yeah. Yeah, a circle with spikes. I mean, that's pretty much what we're looking at. We're looking at needle-shaped crystals, and that's because of the internal lattice that we just saw of those crystal features that forms those particular needle shapes. So this super fast reaction is going to continue basically until this entire bottle is fully crystallized. And it goes pretty quick, as you can see, forming these needle-like crystals. Great. All right, so now it looks like our sodium chloride has finished evaporating. So we're going to move on to the sodium chloride and look at that under the microscope. Yeah. All right, so who wants to yell out what type of shape they see here? Yeah, I heard some squares. Yep, that's exactly right. So sodium chloride has a cubic lattice, which is why it has formed these square-like shapes. All right, great.
Thank you, Samantha. That was great. Thanks, Samantha, and Janine and Katie again. And the movie is just a replay of the kind of crystallization that happens. Okay, so we now want the children to try to illustrate for us what it means to be on a crystal lattice. We've shown you something that looks like squares, and we've shown you something that looks like hexagons. And we have on the floor a pattern of dots, and we're going to have the kids now help us understand what a square versus hexagonal lattice is. So if you would like to come down and stand on where I am on this side of the room, and then we're going to see if your parents can recognize different lattices. Okay, we'll stand over here. Everyone has to come over here. And some of you, you're getting a little present. Okay. Oh, that's a lot of you. Oh, that's a lot. Oh, that's a problem. All right. Okay, let's go quick. Good. Okay, can I get your attention, please? Oh, for the parents, they're getting a little wrist bracelet. That's just a little present from us to them. Okay. Okay, you guys have to pay attention. Okay, so we're going to do this. You saw that if you start as a liquid, things are liquid. You know what a liquid is. But when you form a crystal, you stop in place. All right, so what I'm going to ask you to do, can you guys hear me? There are a lot of you, but we're gonna have fun. What I need you to do now is walk slowly around the room, okay? But towards the other side where you see the green dots. I just want you to walk slowly around, and when you walk slowly around, you're like molecules in a liquid or atoms in a liquid. And when I say the special word's gonna be solidify. When I say the special word, you stop on a green dot, okay? And if there's more than one of you on a green dot, that's okay. Okay, so mill around, walk around, you're in a liquid. See, they're all in a liquid. Everyone see that? They're all in a liquid. Walk around, there's a lot of room over here. Walk around, and when I say solidify, I want you to stand on a green dot. So walk around, you're all in a liquid. Walk around. Okay, now solidify. Find a green dot, and if you find a green dot, if there's more than one on a green dot, that's okay. For parents, that's called a defect in material science. Raise your hand, maybe. Let's see if the parents can see where there's a square lattice for where there's a hexagonal lattice. Can anyone see? Or does it just look like a mess? It's an experiment. Okay, there's supposed to be a square lattice on the left side. That's not so bad, by the way. Yeah, you can see one over here. There's a nice hexagon over here. There's a hexagonal lattice on the right. So thank the kids again for making a nice lattice for us. 2 nice lattices. Thank you again. You can go back to your seats. Okay, you did great. Okay. And you got a holiday present. Okay, back to your seats. Back to your seats. All right. So that was an attempt to have children appreciate a little about shape. So now we have a demonstration that is also going... Okay, now we have a demonstration that has a very beautiful piece of geometry to it and will change the way you shop if you stick with us. Okay, so we have a box in front of the room. The box, if we get a camera on it, the box is filled with ping pong balls. And I need everyone to look at this and tell me what they see, what kind of pattern they see in the box. Okay, so here's a box. It's all filled with ping pong balls. What do you see? What kind of pattern? A square pattern. Okay, Essen's going to help us. Okay, the instruction is shake the box in the plane. Okay? So what Essen's going to do for us is just try to jiggle the box fairly robustly in the plane. We're going to try to shake up the ping pong balls. Oh, that was a little rough. Okay. Okay. All right, Essen, you can shake a little more and maybe stop. Everyone agree that, okay, stop, that's good. Okay, everyone agree that box looked filled before with a square pattern. What kind of pattern do you now see? There are lots of places where you see a hexagonal pattern, and there are lots of space. So Essen, you're allowed to add some more ping pong balls. So in other words, by shaking this or disturbing it, you've made space that wasn't so obvious. And the hexagonal pattern allows you to put more balls in the plane. Everyone see that? And you can see very nicely there are lots of places where you have basically hexagonal structures. So let's thank Essen again. You did it perfectly. Okay. So If you appreciate what you just saw, I'm now going to ask you the shopping question. You go to the store and you see two different packings of oranges. On the left, what kind of packing do you call that? A square packing. On the right, what do you see? Hexagonal packing. Now there's a quiz, okay? Who wants to buy box A and who wants to buy box B? Okay, so who would like to buy box A? Box A has a square packing. Who wants to buy box B? There you go. By shaking box A, you get more oranges in the box. You get about 10% more oranges in the box. So in fact, the hexagonal packing is a better packing for the consumer, not necessarily the person who's selling you the oranges. Okay, so that's a little idea about patterns and shape with a quantitative character. Okay, it turns out even really talented scientists think about how things pack. This is a picture of two Princeton scientists, Paul Chaikin on the left and Sal Torquato on the right. Paul is now in New York. They got very interested in packing of unusual shapes, and they chose M&Ms so they could eat their experiment when it was over. But so there are many interesting questions you can ask about packing. Okay, so here's one that comes up at breakfast, an idea about a pattern at breakfast. How many of you like cereal? How many of you like Cheerios? Okay, we need a child that likes Cheerios. All right, you're in the first row. Well, okay. We're now going to do a little quick experiment with Cheerios. This is a breakfast question you have. There's a big bowl of milk in front. What's your name? Lila. Lila's going to add some Cheerios, and we just want you to sort of observe how they arrange themselves. Okay, so Lila's, you're pretty aggressive about adding Cheerios. Okay. All right, so now I want you to look, we'll just shake it up a little, Janine, there you go. And now we'll just look at the Cheerios, and I want you to ask, what kind of packing do you see? Is it a square packing? Does it form stripes? You know, what kind of packing do you sort of see in this arrangement of Cheerios, at least where they don't overlap? You can sort of see, let's just stop there, Janine, that's good. You can kind of see that around every circle, you start to see 6 circles. There's a pentagon. This one's pentagonal. Over here, hexagon, right? 2, 2, 2, 6 around every one. So the packing you see with Cheerios in cereal is roughly hexagonal. Again, because you're decorating a plane. Okay, Lila, how did you get back so fast? Thank Lila again. Okay, so here's a case where if you pay attention at breakfast and you're not eating too quickly, you see a pattern, okay? Well, there's more. Okay, butterflies. Who likes butterflies? Okay, not only are butterflies beautiful, but they tell us something about shape that you all recognize, but it has very profound implications. If you look at the butterfly, what's special when I look at this butterfly? No, Lila, you helped us. All the way back, right there. Yeah, it's symmetrical. By that you mean the left looks similar to the right. If not, it even could look identical to the right. When that happens, we say there's a plane where the left and right are the same, and we use the word symmetry to refer to that. Lots of butterflies, lots of nature, and people even. Lots of nature has this feature. Here are butterflies. And you see they all have a left-right symmetry. Some have stripes and spots. Some just have spots. But they all have a symmetry to them. When it's the same left and right, we use the word bilateral symmetry. It's a nice word. So now what we're going to try to demonstrate that to you is with a mirror. Okay? So here's the idea. We'll see if this works. This is a mirror. Everyone, you have a mirror at home. This is a mirror. Okay? Okay, as soon as I put it in front of me, you can only see half of me. You can't see my right side, right? But if we get the angle right, Hakeem, you can help me. Do you see all of me? Yeah? So if you get the angle right, you should be able to see not only my left side, but you think you see my right side. Is that right? And that's because we're effectively symmetric. Now, my family will tell you I don't have a good right side, but you don't see it. You just see the reflection, right? Is that clear? So mirrors have a feature of mirror symmetry or left-right symmetry. Could you guys see over there? Those okay? All right. So just for fun, because we were using a mirror, we're going to do a very nice extra demonstration for you that is a little related to patterns, but it's another feature of a pattern. So I told you about the mirror. Because we were using mirrors, we decided to just show you something cool that involves a laser and a mirror. Okay, so Janine has up front, we have a mirror. Oh, we also have this thing. Do kids recognize this? What's this called? Measures angle. It's called a protractor. We have a large protractor, okay? We have a mirror, and we have a laser. You can see the laser point, but you can't. Can you see the laser beam? No, you can't. So we're going to help you see it, and we're going to do it in a way that helps you see how a laser beam bounces off a surface in what's called reflection. So Janine has a fog machine. It makes a fog, and we're going to now turn the lights down. Okay, so first we're going to turn the lights down. Then we're going to shine the laser. You don't see it because it's bouncing off the mirror, but Janine is now going to add the fog, and what you see is that the angle, a physicist would say the angle of incidence coming in, you can see that it's the same as the angle that's bouncing off. Does everyone see that? So there's this beautiful, if you like, symmetry associated with what you'd call the reflections from a mirror. And where you take advantage of reflections from a mirror is in this thing that's called a kaleidoscope, which many of you have looked in. A kaleidoscope makes optical patterns for you. And those are because there are many different reflections off of many different mirrors. And so kaleidoscopes form these amazing patterns from all of these kinds of, if you like, reflections. So there are many different places where you can look for other kinds of patterns. Did you like that demonstration, by the way? Was that helpful to you? Okay. All right, so you see this left-right symmetry many places. You see it in architecture. Who recognizes this? Yeah. Yeah, it's the Taj Mahal in the north of India, built 400 or so years ago. It has this beautiful left-right symmetry. To tell you about symmetry in flowers, my colleague Katie Wu is going to tell you a little about the beautiful features of flowers.
Hi, can everyone hear me?
Loud.
All right, cool. So we're going to find another example of symmetry in flowers. So plants are broadly classified based on how many seed leaves or cotyledons they have. Monocots have one seed leaf, and they typically have flowers with multiples of 3 petals. And dicots are plants with 2 seed leaves, and they typically have flowers with petals in multiples of 4 or 5. And so here is an example of a monocot. It's the crocus flower. It's the first flower to bloom after the winter, so you might see those in a few months. The crocus has 2 sets of 3 petals, and it has what we call threefold symmetry. Other flowers in the monocot category have 6 petals, but they have what looks like sixfold symmetry. And so in contrast, here's the buttercup, an example of a dicot. The buttercup has 5 petals, right? You can count them, there's 5. And that's similar to other flowers in the category of dicots. They all have 5 flowers, and they have 5-fold symmetry. And so when 5-fold rotational symmetry. So when I say rotational symmetry, I mean that we can achieve the same exact shape after rotating something by a partial turn. So here, we have a sketch of a flower. We say that this flower has 6-fold symmetry. And that means that if we rotate the flower by 1/6 of a full turn, then we'll have the same exact thing that we started with. Right, so next time you go visit a garden, take a look at the flowers that you see and count how many petals they have and try to look at the rotational symmetry that you find there.
Perfect. Thank you, Katie. So this was meant to get you thinking about nature, and we added one more word, the idea that you can have a certain kind of rotational change, of rotational symmetry. Okay, so now we're going to try and show you a little bit more about the world that's interesting because of the way it can change. So Janine has an experiment with a piece of plastic in front of the room. It's the red sheet you see there. There's nothing special about it. It's soft. It's a piece of plastic. And we're going to place it between two plates. And a scientist who studies it, or a mathematician, would say it's the same everywhere. It looks the same everywhere to you. It's homogeneous is the word they would use, big word. It's the same everywhere. But Janine is now going to compress it on the two sides. She's just going to squeeze it slightly. And when you squeeze it slightly, you have to ask, what do you see? And do you see anything happening to the sheet? Maybe, John, can you turn the lights down a little? Maybe? Ooh, the audience got nice and quiet. Yeah, so can you see a pattern appearing? So when you compress the sheet, you start to get a pattern. And what kind of pattern does this remind you of? It looks like stripes. They're horizontal lines. We've added a little picture so you can see it here from the side. That's good, Janine. That when you compress it, you start to get a pattern appear. So you might call them stripes. Someone might call them that it buckles. It forms this nice shape. And a mathematics person or a physics person would say you started with something that was the same everywhere, but then something appeared, a shape appeared out of it, and they might use the word breaking of symmetry. It doesn't have the same shape it did to start with. Now, this kind of idea is something that if you have your lunch boxes that we gave you, we have two little demonstrations in there. One of them, Zhang is going to lead you through now. There's a piece of plastic inside. You can take that out, and Zhang is going to talk you through a quick demonstration you can do at home and on yourself.
Okay, hi. If you look inside the box that we gave to you,
louder, Zhang. Clearer, louder.
Yeah, you'll see a piece of plastic sheet that looks like a smaller version of this, and we'll show you what you'll be doing. Can you help me? So here, we're going to stretch the plastic sheet laterally, and you can do the same thing, and you'll see wrinkles appearing, the vertical stripes that appears on the plastic sheet. So you can try the same thing and see if it forms. There you go. Okay.
So everyone try to stretch the sheet, and you'll start to see a pattern appear.
You'll see the similar thing as you squeeze your skin. You'll see wrinkles appearing.
You're too young, Zhang.
Thank you.
Yeah, so if you squeeze your skin, and it might be an age-dependent feature, you'll see many also wrinkles, the same thing. So you stretch a sheet, it goes from being uniform to having stripes. You can squeeze something, you get the same kind of feature. Those are patterns that appear when you change something. Zhang, thank you again for that. And if you look around nature, you find even different kinds of animals. Here's the Shar-pei that has a wrinkle-like feature to its surface. Okay, so there are even puzzles in nature. Here's a scientist at the University of Toronto who noticed something funny about icicles in the winter. He took different pictures of icicles. Some of them were smooth. Some of them have this stripe-like pattern, sort of like we just showed you. And then he noticed something. He doesn't understand why, but he did notice that when you use only what's called distilled water, you take all the ions out of water, and you make an icicle, it has a smooth surface. And when you use contaminated water or tap water or water with salt in it, it forms the striped pattern on the right. And he just wrote about this and doesn't really understand anything more. So you see, they're puzzles about how some patterns appear in nature, even with very ordinary materials. Oh, now we've got something really great for you. So Samantha's going to help lead you through first a demonstration we do up front, and then in your lunchbox, there, Sam, in your lunchbox, there's an experiment you're all going to do. It's going to give you a Christmas present or holiday present to take home for you. And, but first you're going to see a large version of it, and then you're going to do a small version, and the parents have to help because it involves paint, and we don't want the whole room to be filled with paint. Okay, Samantha, over to you.
Great. All right. Yeah, so the next demonstration we're going to see is going to show some beautiful patterns. So what we have here are 2 pieces of acrylic. And what we're going to do is take some paint. We have 2 different colors. And we're going to put very small drops kind of right in the center of it. So you can see it up on the screen. All right, so just a little bit of paint and like some different patterns to make it exciting. And so next, we're going to take the second piece and smush it right on top of that paint. So as it flattens out, and they're putting quite a bit of pressure on this, it spreads in a circular front is what it's called. So it forms kind of a circular shape, and they're really pushing as hard as they can because the flatter it is, the better the pattern is going to turn out. So once it's pretty flat, they're going to rotate the top plate a little bit, and that's just to help get a grip to remove the second acrylic paint. And then when they remove it, they're going to go straight up. So not peeling it, just straight up. Yeah. And you're left with this beautiful branched, what's called a fractal pattern. So in our demonstration, you're going to have the chance to do it yourselves. Again, parents, please help. If you want more than one paint color, we encourage you to share with your neighbors. And again, when you pull them apart, try and do it as straight up as possible.
Okay, we'll take a couple minutes now, and you can do your own demonstration at your seat. Nervous. Okay, while you're kind of finishing up, I'm just going to keep us moving here for everyone. I hope everybody enjoyed that. If you look, you now have 2 sides. They'll dry, so you have basically 2 presents. If you're from a family where you have a Christmas tree, you'll notice that Katie made every one that has a little hole in it at the top, so you can hang it if you'd like, or you can hang it from your window, whatever you'd like. These kind of structures, as Samantha said, are called branching patterns. You see things like that even in your lungs, as I'm about to show you. These kind of features come up many places. Okay, so you've now made this kind of structure. This image on the right, which looks a little like that, we call a branching pattern. This is actually the image of the lung of a developing mouse. It was taken in the laboratory of Celeste Nelson. She works with Andre Kozmerlich here at Princeton. So you see these kind of features many places. And you made sort of a version of it that had an artistic feature to it. We have another kind of demonstration that forms a pattern that you can do in your kitchen if you're very, very careful. Janine is getting it started up front. It's a layer of liquid in a pan. She uses a Petri dish. And it's placed on a hot plate to make the liquid warm. When you do that, it turns out the liquid doesn't stay stationary. It starts to move around and it makes a pattern. So let's just see what kind of pattern forms in this layer of liquid that you just saw Janine put on the hot plate. What you can't see is that the liquid is moving, but it's leaving an imprint on the top surface. And you can start to see it makes lots of little structures. And you might even see that some of them look like what kind of shape? What kind of pattern? You can count 6 objects around the center circle. You start to see things that look like hexagons in the plane, even though it's only an image of what the fluid's doing down below. So there are many cases where you see patterns where you wouldn't expect there should be a pattern, but nature makes a pattern. This kind of phenomena where you see patterns in heated systems, which comes up in nature, they were first observed 100 years ago by a man named Henri Bénard. They're common. There's a feature in science that has his name to it, and if you do this in your kitchen carefully, you'd be doing a form of the experiment he did. And if you look carefully at these patterns, again, you see many features that have hexagonal-like structures. Again, a geometric pattern. This kind of thing happens even where you don't expect it. So I'm showing you something that appeared in the news. I think it was just from CNN, and it made the physics news. It appeared in February of this year. A photographer was in the desert. Okay, the desert only has a little water. Most of the water evaporates. When it evaporated, it leaves behind salt, and it turned out these rims of salt all look like they're making polygons. Even here, look, you can count one. It has effectively 6 or 7 sides. Here's one with 5 sides. It makes hexagonal-like structures. They're huge. They're 1 meter across. They're half the size of you and I. And the scientists got interested, how do these patterns form in the desert? And they realized that there's water down below that's doing what your pan did. But when the water near the top evaporates, it leaves the salt, and the salt is marking something about motions under the surface that you can't see. But what you do see is a hexagonal pattern. Okay, now ready, there's more hexagons. You see hexagons everywhere. So the beehive, hexagons, right? Bees live in hives, they raise their young in hives. The hive has to be strong enough to support the weight, and it has to carry the food for the nest of bees. That form, that structure that does it best, apparently, is a hexagonal pattern. If you like the outdoors and you go hiking, and you go to a place in the West called this thing called, you can see what people thought of it. They named it Devils Postpile National Monument. Well, they named it Devils Postpile. The government labeled it a national monument. This is tens of meters, many tens of feet high, solid columns. The columns, if you look at from the top, are 5- and 6-sided. They're most often hexagonally shaped. When the rock solidifies, it solidifies as a long hexagonal column. So you see hexagons in the geology. You see hexagons everywhere. And it's not only in America. If you go to Ireland, the same phenomena happens. There it's called Giant's Causeway. So these kind of phenomena that lead to shapes and patterns, often in terms of hexagonal things when you have planar structures, are common. Okay, so this is a real experiment because we have no idea what's going to happen. But what we'd like to do is use your children to illustrate the idea of branching. Branching for the children is this. The lung is branching. If you've been to a mineral museum, you might have seen the branched patterns that you sometimes see on fossils and other structures. We're going to try to have the children illustrate how a branching pattern happens. But it's an experiment. So if the kids would like to participate, come down and stand on the side of the room where I am over here. And I now need some adults, so you guys at back, I need you to help. Okay, you're Lily? What's your name? Lila. I got close. Okay. So stand down over here. Okay, you guys wait here. You wait here. I need the adults. Okay. Sivan, do you want to help me? Oh, okay. Okay, got it. Udi, can you help me? I need, okay. Okay, so, wait a second, there are 4 of you, and Udi, 5. Okay, good. So, we have 5 adults on this side of the room, okay?
6?
Actually, okay.
Did you ask for
No, that would,
My son
6.
wanted me.
Okay, yeah. Okay, so we have, what's your name?
Eric.
Eric. Okay, so we have 6 adults on this side of the room. What we're now going to see is, can we create a structure with 6 branches, okay? You got it? We're starting with 6 adults. A scientist would call them a nucleation site. Okay, so the kids, this is what you have to do. What you're going to do is you're going to walk slowly across the room. When you come to an adult, you stop and turn around and look at me. Okay? And the next child, your goal is just find the nearest person you can and stand by them. Okay, that's the goal. Forget the adults. Just stand by them. You got it? You walk slowly, you see someone, you stop, and you try to form a line. Okay? The ones in front, I want you to find an adult, turn around, look at me, and then someone will stand by you. Okay? So now we're going to try to illustrate how branching happens in nature. Walk forward and stand near the first person you come to. Follow them and start to stand near the first person. Slowly, slowly, walk slowly. Walk near the first person and then stand near them. You got to form a line. And now the question is, are they going to form 6 lines or something else? Well, it's clearly something else. Okay. All right. So let's just stop. But I think we got it. Okay. What you see here, first of all, there's a defect on the right where there's no adults, but that's okay. What you see is there's 6 adults to start. But what comes out at the end are effectively 1, 2, 3 lines out front. Everyone see that? That's the idea of branching. We've lost a few lines. They're back in here. They didn't grow. They stopped because the people started here. That's effectively the idea of how branch patterns can form in nature. Everyone see that? Actually, the experiment sort of, from my perspective, you guys were brilliant. Okay? That was great. All right, so thank them again. And you guys were great nucleation sites. Thank you. Okay, there are... Okay, there are a couple short stories I would like to tell you at the end if you have 5 or 6 or 7 more minutes. The stories go like this. We just told you how things branch. We had the kids sort of do this. I now want to tell you a little about stripes. And I want to tell you one of the great chemical stories in history. So, on the word cloud, many of you pointed out zebras when you thought about patterns. Zebras have stripes. Well, many things have stripes. Skunks have stripes. How many of you like beetles? Beetles have stripes. The Princeton tiger has stripes. But you can see stripes in other places. If you look out the window when you're flying in an airplane, you sometimes see patterns in clouds. That has stripes. Many things have stripe-like structures. I also showed you a couple earlier today. But not all animals have stripes. The giraffe, you'd often say, hold down the sound from these wrinkly things, actually, if you can. The giraffe has more like a spot-like structure. Other animals have spot-like structures. The beautiful peacock has spot-like structures. How do you form such patterns that might be stripe-like or spot-like? Where does that come from? And one idea where that comes from is chemistry. And the name associated with it, this chemical pattern, is named after a person named Alan Turing, who is the first person to recognize how chemistry might lead to these interesting patterns. Alan Turing was one of the great intellectuals of the 20th century. Although born in London, he did his PhD at Princeton. You might think when you read first about him that he was a mathematician. Some will call him a computer scientist. He was good at breaking codes. Some refer to him as a philosopher. But it turns out he wrote one of the most important papers in chemistry and biology by recognizing how simple ideas can lead to patterns. Now, when you read about him in history, what you normally learn is that Nazi Germany had a machine for making codes called the Enigma machine, and Alan Turing was one of the people responsible for breaking that code, which was instrumental in World War II. But Alan Turing also did this. He showed you how chemistry, simple chemistry, can make patterns. And we're now going to try to illustrate that for you. So Janine has prepared the kind of chemistry that's involved. It only has a few chemicals, but the ideas are sort of complicated, so we only will touch on it. But in this dish, we're going to place a solution with Bromine is a main component. And then there are a couple other chemicals, and you have to be able to see something, so a chemist will add what they'll call an indicator. And what we just want to show you is how this system, which looks completely uniform, you'd say it looks homogeneous. Now if you wait and some chemistry, some chemical reactions start to happen, you have to ask, what do you see? Okay, so there's the first indication that something's happening. Here's something else. So do people start to see something? What do you see? Yeah, you start to see spot-like structures coming from chemistry. And at some point, other patterns can take place. So this is a structure that's associated with a chemistry that's named after two Russians. The video I'm about to play is just a sped-up version of what's going on up front. In the chemistry world, this is called the Belousov-Zhabotinsky reaction, after two scientists who in the 1950s and 1960s discovered this. Nobody believed them, by the way. It took a decade or two before people understood what they had done. And these structures form circular-like, spot-like patterns. They can form line-like patterns. They have the feature of where stripes and spots can come from simple chemistry, relatively simple chemistry. This is an example that's common in chemistry classes. Okay, so what does that have to do with things? I'm going to skip that. Many animals, I've just shown you, have spots. But it turns out that, and you can read online if you want about this, that people have discovered in biology that the change of one gene can make the spot-like structure of the cheetah become a stripe-like structure, although this animal has stripes and spots, right? So there are many possibilities, and very recently, two Princeton alumni recognized some features of what are called the Turing pattern, and how it can be, if you like, made sharper, if you like. And so they studied some of the chemistry behind this fish, which is called the ornate boxfish, which has stripes and spots. So these are areas of active work where people try to understand where patterns come from. Finally, one last demonstration for you, because it's the holidays. If you're from Europe, there's a kind of ice cream called Viennetta ice cream. It's a mixture of ice cream and chocolate. And the way they mix them up is they have a machine that automatically has this wavy-like structure to it. It just automatically does this. And then they package it and they sell it to you. So we're going to show you how you might get things like this in your own kitchen. All right, so I think I need a volunteer to squeeze icing. Who's good at making cakes? You're good at making cakes? Really? Okay, then you have to come help us. Okay, what's your name? Emma. Emma? Emma's going to help us. So we have some icing up front. Okay, you should pay attention because this will make your holiday intellectually interesting, okay? So Emma's going to first show us, no, Emma, we need a little, Janine's going to help you. We're going to ask you the following question. We want you to pretend you're decorating a cake, and how would you form a pattern on the cake? And how would you make curlicues? Yeah, you're doing great. Yeah, it's true. I should talk to your dad. Yeah, Emma's good at decorating. Okay, good. So everyone see that? She's moving her hand to create a pattern. Everyone got it? That's what you'd all do, right? Doesn't that make sense? Okay, Emma, that was great. Thank you. Thank Emma again. Okay, so we're going to show you. Okay. We're going to show you another idea, Emma, that you could do. Okay, so what we're now going to do is show you how you might choose to decorate your cake without moving your hand. Okay? So we're going to have Emma just squeeze the tube so that the icing comes out, and we're going to rotate the plate. Okay? And if you rotate the plate, the tube, the icing layer makes a pattern. And if you can rotate it at a very constant speed, you'll get a very regular pattern, including curlicues. Isn't that great? That's just by rotating the plate. Okay, and that's a pattern in front of you. That's actually studied by my colleague P.T. Brunn here in engineering. Okay, thank you, Emma. Thank you, Janine. That was great. Okay, so we're at the end. It took a little long. So what have we tried to show you? We tried to show you lots of patterns. They come up everywhere. And if you're interested in science, they come up in every field of science, from biology to chemistry to engineering to physics to math. They're everywhere. They're all around us. You just have to open your eyes. And if you're interested and you want to go read, it turns out just a few months ago, somebody discovered a new pattern that no one knew about before. I'll let you go read about it. In closing, I just have a lot of people to thank. We stole this idea of a holiday lecture from Michael Faraday, the great English scientist. This was a team effort between Harvard and Princeton. You've seen lots of people participating. Janine Nunes is a key part of holding everything together here. You've all had email from Sonia, and many of the people here contributed. And so finally, I just want to say thanks to all the people who supported it, and have a happy and safe holiday season.